All right, 105. So we'll go ahead and start, and I'll do a quick introduction. I mean, I should have Damek here. If we had a double screen, we could both be doing this since we're both advising you. But let me just say a few words. I mean, it's been fantastic having Ben around as a colleague. He came having done combinatorial optimization as an undergraduate, but pretty quickly switched over to first order methods, but in really a variety of settings, both convex and non-convex. He's worked separately with Damek, with me, but also with Li Jun, Matteo, and Sean Liu, who's a student of Rob Freund's, who's now at Chicago Booth. So he has very sociable personality, very outgoing, lots of interest, extremely independent. He's really been his own thesis advisor. So he's already had 4 papers that have appeared in top journals, and there's another half dozen or so in the works. So he's doing really well there. Yeah, and let me say, sociably, I got to know Ben really well when he and Damek was there for a while too at Simon's in fall of 2017. And so especially after the first part of the semester, Ben and I would meet almost every weekday, and on weekends we'd often take hikes several times out at Point Reyes, which absolutely fantastic. But that's where Ben told me one of the most surprising things about him, and I still can't quite get over it. So I don't know if you know this, probably some of you know this, but Ben, when he was an undergraduate, one year he was the president of his fraternity. Now, I don't usually think of students working with me having even been in fraternities, much less being the president, but anyway. So, but it just goes to show just sort of how sociable he is. I should also add it was an alcohol-free fraternity. So explains a little bit better. All right, so Ben, please take it away.
Awesome.
I should also say one more thing. So his thesis consists of 7 chapters, which are really 7 distinct papers. And there's no way in this time he can make his way all the way through that. So let's see what he chooses to do.
Great. So this should be sharing my screen. Hopefully that is up there. And let me change it so I can see some more of your faces. There we go. So yes, my thesis is talking about a lot of different things, and so my hope today is to give some flavor of a lot of the high-level results, and then dive into one thing in particular, kind of picking out some favorites. But this work is with a lot of different people, like Jim said, and so I'll kind of give some thanks along the way and point out my co-authors there. But otherwise, let's jump in. And I want to start by kind of restricting down our focus. So instead of talking about generic first order optimization to give a high level scan, I just want to think about one algorithm for maybe the first 20 minutes, this subgradient method. That's really the simplest algorithm you can kind of do for first order optimization. And so that'll let us get a picture of the results throughout this thesis, but kind of at a very high level, what this method does, we think about a convex optimization problem. So you want to minimize some convex function f of x over a convex set q. Well, how do you minimize a function? Well, you move downhill. And so the idea for our algorithm, for this very classic algorithm, is to linearize the objective. That's where first order is coming in. We kind of take a first order Taylor model and move downhill on this red line that kind of approximates the function. And if we became infeasible, move back to the nearest feasible point, which I can't really draw constraints that well in a 1D picture. They're not that interesting, but we just move downhill and come back to being feasible. And repeat that process until you're near the bottom of the function. So kind of formalizing that, these linearizations are called subgradients. So it's just a linear function that is underneath our convex objective. If we were differentiable, this would just be exactly the gradient. And so, this notation of it being a set is just here to allow us to have corners on our function where maybe there are many ways to linearize. Any one of them will do for us. And then getting back to being feasible, we'll do that with orthogonal projection, which just says move to the nearest point that's feasible. So find the x prime that's feasible closest to your current point x. But then using these two definitions, the algorithm is then just repeatedly move in the negative subgradient direction, some amount alpha k, and then project back to being feasible. And you just do that loop on repeat, and it ends up working really well. So this method's been around for a long time. Polyak gave maybe the cleanest analysis for this back in the late 60s, which says that if your objective is M Lipschitz continuous and convex, then if you take this step size that's often called the Polyak step size, you'll get that the method converges as you take your length that you run it out to infinity. So the objective gap we've seen is shrinking like 1 over square root of t. So for t big enough, you get arbitrarily close to optimal. And then in the 80s, it was shown you can't do better. So for these M Lipschitz convex functions, this is the best you can do. And so in a sense, this is kind of the optimal method. There's no point in looking farther than the subgradient method. It has matching upper and lower bounds. And then just to do the theory kind of one better, if you additionally have some structure like a growth bound, so this is often called like strong convexity.
My buddy's doing his PhD defense, so I just want to watch that. Start with it.
David, you became unmuted. Okay. If you have some extra structure, like here, this is quadratic growth. It says your objective gap is getting bigger, at least quadratically. Then you can get a faster convergence rate. So you'd get a rate that looks like 1 over t. If instead of this growth being quadratic, you had some other exponent, you'd still get a better rate. And again, in the 80s, shown that you can't do better. So even for these kinds of setups, the subgradient method is the optimal method, matching upper and lower bounds. So in a sense, this theory is really nicely tied up. What's left to do? We can view a lot of the chapters of my thesis as nitpicking this and having some more criticisms saying this doesn't tell the whole story. So I have kind of 5 criticisms here that roughly line up with chapters of the thesis. So I want to take this first chunk of time to, at a high level, go through some criticisms of this classic kind of analysis. And then critique number 5 we'll spend a good chunk of time doing in detail. But my first criticism is that Lipschitz continuity is a big assumption. So for an objective function to be Lipschitz, it kind of has to grow linearly. Asymptotically, if you run away, you're bounded at increasing it at most the rate your Lipschitz constant gives you, which means you can't do things like least squares or very classic regression ideas. Those grow quadratically. So lots of natural functions we want to look at don't have this linear growth. And so you have to chase your tail some, trying to come up with what constant works and do some local argument. But being based on Lipschitz continuity sends us kind of, it ties our hands a bit. And so a solution that I kind of offer to that criticism is in this 2019 paper, which says it's good enough to have any upper bound of the form bounding the objective gap by some function of how far you are from a minimizer. If you have a bound like that, we get a convergence rate that uses that same function d that will go down to 0 as your step size increases. But depending on the upper bound you have, you get a different rate. So if you were Lipschitz continuous, then Lipschitz continuity would say that this objective gap is bounded by just your Lipschitz constant times your distance. So this d function would be a linear function, Lipschitz constant times the norm inside. And so if we plug that in, if we take d of t as just m times t, then you immediately get Polyak's convergence rate back. You get this 1 over root t rate. So we've recovered that right away. If you go to smooth optimization, if your objective was nicely differentiable, then you can make an upper bound that looks like a quadratic, because the objective had to flatten out at optimal. And then if you kind of take your second order Taylor model, you would build a quadratic upper bound on the function. And so we get a faster convergence rate right away from that, we get this 1 over t rate. It's very classic as what gradient descent does, but kind of the argument we get to it, here with doesn't use smoothness or some kind of descent. We're just using, oh, here's a different upper bound. So, this nicely gives those rates. Particularly something fun that comes out of this, we get what I like to think of as a superposition. My brother's a physics PhD, so the more I can steal the language from physics, the more it annoys him. So I think of this as being like a superposition. If you had an objective that was Lipschitz in one term added with another term that's smooth, well, the upper bounds would just add together. If you have an upper bound on each part of a sum, you have an upper bound on the whole sum. Well, and so then we can just apply our theorem, and you get that the convergence rate guarantee for the sum of Lipschitz and smooth problems is just the sum of their separate guarantees. So you can think about the system in its components, and if you understand the cost of each component, you just add them together, and nothing can kind of compound or go poorly in the problem setting of Lipschitz plus smooth. So that kind of falls out of having this alternative to Lipschitz continuity. So we can get more interesting things if we go beyond looking at that box of Lipschitz continuity. My next criticism is that most applications or many applications are not convex, especially the kind of modern machine learning setup. And so in work early in my PhD with Damek, we worked on an alternative to using convexity to analyze these subgradient methods, which we settled on kind of this row weakly convex idea being the right tractable thing. So there we have that a problem is row weakly convex if adding a quadratic to the objective would make it convex. Kind of geometrically, what that's doing is it says at each point on your function, you can draw a quadratic underneath the curve. And so you kind of have bounded negative curvature. You can't turn down very quickly, but you can still make very generic non-convex shapes with this. You just have kind of limited curvature. But for these weakly convex problems show up pretty generally. We were just thinking about sums. So if you had a sum where one of the terms is smooth but non-convex, and the other term is non-smooth but convex, then together that sum doesn't have smoothness and it doesn't have convexity, but overall this would still come out weakly convex. And so kind of our theory there is still going to apply. And likewise, if you have a model that's a composition, you still have weak convexity hold. If you have some smooth mapping that you compose with a convex function, that would show up if you had some, if you were looking for a low rank matrix and your variables were two skinny matrices U and V, this smooth mapping inside might be taking the matrix multiplication of U and V to construct your big matrix. That would give you some nice smooth operation inside, but low rank kind of problems are very non-convex. So on the whole, we don't get a convex problem out of that. But for these problems, Damek and I gave a really simple conceptual algorithm that works for these. Repeatedly, we want to add in a quadratic centered at the current iterate and solve this now convex problem, because weakly convex problems were exactly the ones where adding a quadratic would allow you to efficiently solve the resulting optimization problem. So you repeatedly solve this convex problem, which we could do with the subgradient method. That gives us our next point, xk plus 1, and then just repeat that loop. So we can give some kind of subgradient method like that, and we can gloss over the details with kind of big O, but if you had a nice Lipschitz weakly convex objective, then after a bounded number of iterations, 1 over epsilon to the 4 is pretty big, but after a bounded number of iterations, you would have some iterate that is nearby the set of nearly stationary points. So kind of this type of algorithm gives you a tractable way to handle these non-convex problems, but still get good theory. Criticism number 3, flying through chapters. It's hard to pick a good step size. I had that kind of magical step size in the theorem before that was Poliak's step size. You can pick more implementable step sizes, but it's always kind of problem specific, or you need to have a grasp on the geometry of what's going on. to pick a good step size. Because if you pick it poorly, you might try to go downhill but move far too far, and you actually increase your objective value by a lot. And things could be unstable if you don't pick a good step size. But there's a really classic type of algorithm, bundle methods, dating back to the 70s, that have the property that they'll converge no matter what. So no matter how you configure it, as you iteratively do your updates, these algorithms keep a bundle of linearizations. So they have many linearizations of the objective that allows them to prevent themselves from running off in a bad way, right? So if you just had that one cut from before on the left, you might run off to the right side thinking you're making progress. But if you kept some other linearizations, those would kind of inform you not to go farther than this to the right. So keeping more cuts lets us more intelligently move downhill. And so these are known to be stable and have been around for a long time. And recently with Mateo Diaz, we showed that these can get the same optimal convergence rates as the subgradient method, while being kind of more stable and not having these same step size issues. But getting into those is kind of beyond what we can do today. And then my fourth kind of high level criticism before we'll dive in on the fifth one is that this kind of growth bounded case, the extra theorem I gave, feels redundant. If you go through the proofs of these kind of things, the proofs often look really similar. And we do it for lots of different algorithms, some kind of better convergence when you have growth bounds. Are those alternative proofs really that interesting? So before we had that if you grew quadratically, you would get this better 1/t rate. And this is done for lots and lots of optimization problems. So I've stolen this table out of my thesis. But if you have these different methods, they all have a rate for general problems, a faster rate if you have some kind of quadratic growth bound, maybe an even faster rate if you have a sharp growth bound, it goes linearly. But we just have tables of different rates for different problems. It's a lot of work to prove all of those. So a kind of solution to this feeling a bit redundant, in one paper, I show that if you have a general growth bounded convergence rate, that will give you a general rate without assuming a growth bound. So in terms of that table, it says that all the convergence rates imply to the left. So if you know the sharp convergence rate for the subgradient method, I would be able to conclude the quadratic growth rate and the general rate, just from a kind of meta argument put on top of that rate. And then in a paper with Jim Renegar, we show that a restarting scheme kind of gives the arrows to the right on this table. So if you had a general convergence rate, you can restart that algorithm and get improved rates for the growth bounded settings. So kind of with those together, if you gave me any one element in this table, I could complete its row out, kind of without having to redo the analysis for each of the other settings. So kind of those together give some sense in which the proofs of these different settings are really doing the same stuff. But those are also kind of beyond what we're going to dive into. Really, the stuff I'm excited to talk about today is my fifth critique, that these orthogonal projections, the way we were handling constraints, those are expensive. And so we want to come up with ways to avoid those. But kind of before we dive into that, which will be somewhat self-contained, are there any questions up to this point?
I guess I have a quick question about the Lipschitz, the first critique, I think, or I'm not sure if it was actually the first. It's just my first question.
Yeah.
So you mentioned that the rates of the algorithm degrade as a function of the distance, and the function is d, the same d there. I wonder whether you have any insight into whether that's tight, and if you actually would see that type of degradation in practice.
So it's tight here in the sense that the subgradient method is optimal. So you could take the lower bound tight example for the subgradient method, and say if you wanted this to be a D as a quadratic, if you take that tight example and square it, kind of set the optimal value equal to 0 and square it, you'll get a tight example where you have this growth bound instead. So kind of the same tightness, in essence, you could take your problem to a power, and that doesn't really change the problem. It doesn't change the subgradient directions that you'll be given. And so, this is tight for every D by the same example that makes the subgradient method tight. Yeah, which is kind of flavored like, in my mind, that's similar to the KL setup, where you have different, reshapings of your objective that keep it equivalent. But if you narrow it down, you can build everything out of the one optimal subgradient argument.
Ben, could I throw in a quick question while you have this slide up?
Yeah.
So I'm sort of curious about the role of the norm in this kind of, so you have these growth conditions, right, which is like some function of the norm. Mm-hmm. So does this sit in some kind of broader class of questions about, you've got growth with respect to some more general function and you deduce something else?
Yeah, there are good questions like that. I don't have great answers. So at least for the proof of this result that, here it's not called a theorem here, but for the proof of this theorem, it's very much using kind of some inner product as the, making this need to be the 2 norm for this proof to work. But I would suspect that if you did kind of these Bregman ideas, where instead of the subgradient method, you're looking at this mirror descent kind of method, then I would find it believable that you'll get something with that reference function that's the right kind of growth bound. But at least immediately here, this kind of needs to be the 2 norm for my argument to go through. Yeah. But yeah, I mean, certainly something with other norms or other kind of geometry should work. But yeah. Great.
And then I guess I have, whoops. So have you thought at all about extending this to non-convex settings?
A little bit. I think you can get something similar if you have the kind of a local region of attraction. If you're in these kind of settings where you have some kind of sharp region where you're sure that the method won't leave this area and come in, then I think there are some arguments that can be made about how that converges in. But somewhat this is reliant, at least in its current form, on the shape at this X star. So unless you know ahead of time in your analysis what point you're converging into, it's a little bit of a non-starter on what should our assumptions be. Right, because I don't want to say that whatever upper bound we have here somehow holds everywhere. Then we're getting back to shapes like Lipschitz continuity. If you enforce that everywhere has this shape above it. Yeah, but at least immediately you would need some X star that you're locked into a local region around. Yeah. Okay, I think we'll jump into the most fun stuff. So my answer, or how to get around these orthogonal projections, is that we can reformulate constraints away by using projective transformations. And so these ideas I'm going to present are all based on an amazing paper that Jim wrote in 2016. And so the details I'll talk about come from these follow-up papers that I have written working with these radial ideas. But kind of at its heart, these things all come from Jim's paper. which was the first thing I really dug into at Cornell and got me to switch from doing combinatorial optimization over to these first order things. So Jim's paper is great. You should also read that. But here we're diving into using this kind of projective transformations that will give us projection-free optimization algorithms. And so I want to start with a motivating theorem, which is only motivating for kind of, in hindsight, this is a good theorem, I think, for motivating where we're going. Like most motivating theorems, I didn't know this theorem when I started working in these ways. So it's kind of only in hindsight good motivation. But projective transformations have a really nice geometry kind of outside of what we're doing here today. But you could think of them very algebraically as they're just fractional linear maps. So if you have some g of z that is a vector linear map divided by a scalar linear, or affine on both of those, that gives you a projective transformation. And the earliest version of this result I can find is from Schiffman in '95, which says that projective transformations are the unique operation that preserves convexity. With some asterisks on that theorem, that doesn't work in dimension 1, and it doesn't work if you divide by 0. So since we're doing fractional linear, you need to stay on the same side of dividing by 0. So in whatever half space keeps the denominator positive, and you need to be in dimension at least 2. But given that you do those, if you have some mapping that preserves convex sets, that's a bijection, then it must be one of these fractional linear maps. So this is, if what you care about is preserving convexity, what you should be thinking about are these mappings. And so we can use this kind of idea of preserving convexity to give a trivial way to reformulate optimization problems. If you had a minimization problem with some function f of x, I could remap its graph to give me a new convex looking problem. And the mapping I want to do is just negate the last coordinate. Okay, well, that's going to turn the graph upside down. And this is a new problem called maximizing minus f of y. That's not a very interesting transformation, but linear mappings are definitely fractional linear. And so we preserve convexity by doing this. But if we look at Schiffman's theorem, it tells us, okay, linear maps do this, but fractional linear maps also preserve convexity. So we should go looking for a fractional linear way to reformulate our problems. And that might give us something more interesting than just looking at the negative. And so the transformation I want to look at does essentially the reciprocal. So instead of negating our objective, I want to do something like take its reciprocal. To make that fractional linear, I have to divide through the whole thing by u. So if you give me some xu, I want to take the height and turn it into 1 over u. For that to be a good fractional linear map, I have to divide the x coordinates also by u. But that gives me an operation like the reciprocal. If I want to apply that to a set, I'll just apply it element-wise. That lets me move sets around in this way that's like doing the reciprocal. You can check just algebraically, if you do this twice to a point, you get back the original point, which is somewhat it capturing this reciprocal nature. If you do 1 over something twice, you get back the original value. This is really nice. It's well structured like all projective transformations are. So if you have a half space, it turns into a different half space. In my picture here, I put in this black line at height 1, and that's the set of fixed points for this mapping. So everything below that black line is getting mapped above it, and everything above is getting mapped below. But that's the kind of shape of how things are moving. If you keep half spaces as half spaces, you definitely keep polyhedrons as polyhedrons. So you map the faces of a polyhedron. It does exactly this, moving from above the line to below. Ellipsoids map to ellipsoids. We have lots of nice structure that comes out of this. So with this very well-defined operation on positive, we have to stay on positive valued things, but as long as your last coordinate's positive, we maintain convexity, and I'd like to get some transformation of functions out of this. And so the idea for how to get a function transformation is exactly what we had before with negating our graph. I want to take the epigraph of a function, apply gamma to it. That'll give me a new set. And ideally, that set looks like the hypograph of something. and my transformed problem will be whatever hypograph that is. So hypograph is everything below the graph. Epigraph is everything above the graph. And so kind of in math, what that's saying is exactly this definition I give here. Take the epigraph and map it using gamma. Then if you want to evaluate the new function at some y, well, search for the highest point that's in the hypograph. So search up on all the v's, looking for the highest y of yv that's in our transformed set. If we transformed into the hypograph of a function, this would exactly pull out that function. On kind of warning message, we need to not divide by 0. That's critical for any of this to take off. And so the kind of functions that it would make sense to do this mapping on need to have their epigraph live in the positive, half space. So the kind of function that's reasonable to look at are functions that map into the kind of extended positive values. I want really our range to be positive numbers, and then I'll use 0 and infinity as the limit objects on that to kind of say that we're out of domain. So if we're maximizing and something is set to 0, that's the lowest possible number that's out of domain. Or if we're minimizing, infinity is the highest number. But the reasonable kind of problems to look at for this reciprocal to be well defined are these positive valued functions. And so an example, just to say that this is a well-defined mapping between functions, if you look at the function square root 1 minus x squared, that's giving us the top half of a ball. And here I put a little subscript plus to say set it equal to 0 when that's not well defined. So everywhere out of domain on this square root is set to 0, but you get that function I'm showing on the left. And if you map its epigraph, everything above that blue curve, you'll get everything below the red curve on the right. And so, pulling out what function is above that red curve, it's exactly the square root of 1 plus y squared. And then our transformation is dual. If you took everything above the red curve on the right, that would map into the stuff below my blue curve on the left. So it goes back and forth, but these two functions are dual to each other under our reciprocal-like operation. And reasonably in kind of optimization terms, I would much rather deal with this function on the right. On the left, we have stuff that's out of domain. If I was outside of this ball, I wouldn't know what direction to move to get improvement. And as you approach the edge of the ball, your gradients and Hessians are all blowing up in size. And so the function on the right has gradients and Hessians bounded by 1 everywhere. So I'd much rather work with that guy. And now in that example, things were dual. I could move back and forth. That's not universally true. So broadly, if you want to apply this twice and get back the original function, you need this property that just kind of, for now is just what's needed. You need this perspective function to be non-decreasing and upper semi-continuous, where this is defined as the mapping of v times your function value at y over v. But if you look at that mapping, you just need to check that it's non-decreasing and upper semi-continuous for every y that you plug in. And those are kind of the critical class of things. So I'll call them upper radial functions. Those are the ones where our duality applies. The word upper here is hinting that there was some arbitrary choice. I could have made lower radial functions. And that essentially comes down to I have a soup in my definition. I could have done things with an inf and kind of done everything from a different side. And you would get a different object. So upper here is arbitrary, just like the soup defining my operation is arbitrary. But the world works either way you define it. We're going to work with this setup. So things are upper semi-continuous and non-decreasing for our duality to apply. On the geometry of what these things look like, we have that our dual will work whenever the hypograph of your function is star convex with respect to the origin. So the kind of shape that guarantees your dual is if sitting at the origin, any ray that you draw will be below the graph, intersect the graph, and then be above the graph. So that kind of shape will make you dual, and if you don't have that shape, you're not dual. So for any concave maximization problem, it's really easy to get this shape. If you just translate your objective to put the origin inside of it, if you had a nice concave shape, it'll wrap around the origin and you'll have this star convexity. But that's the kind of shape of what functions are dual under this reciprocal. And then right away, now that we have functions that are dual, we can get dual optimization problems. And so if you wanted to maximize some function f of x, you could instead minimize its transformation. And the optimal solutions to those two problems are exactly related by our mapping gamma. So if you minimized your transformed problem, just add on the minimum dual value to that and run that through our reciprocal, and you'll get out solutions to the primal, and the primal objective value will be 1 over the dual value. So we have this optimization duality. As long as you have this nice upper radial shape, then I have a new reformulation for any problem we want to work with. And so we can plug this into a concrete kind of problem to show that this does something valuable for us. So I want to think about quadratic programming. So a generic quadratic program will just have some quadratic objective, x times qx plus a linear term over some polyhedron as our feasible region. So all of these ax less than or equal to b. To write that as our non-negative maximization, I need to shuffle things around a bit. So to be maximization, I'm going to replace the objective with this first term, 1 minus our previous objective, and then make it non-negative. So doing that, at the origin, we have objective value 1. We'll optimize from there, but this gives us maximization outside instead of minimization, since we've turned the problem over. And then I want to enforce each constraint with an indicator function. So I've wrapped this whole thing in a minimum where I want each indicator function to be plus infinity when we're feasible and 0 out the objective when we're not feasible. So if you're infeasible for any constraint, that constraint will take value 0 here. And then this whole minimum will be zeroed out, which is our kind of out of domain value. But if you're feasible, all of these indicators take value plus infinity, and this objective will just capture the 1 minus the quadratic objective. So this reformulation is equivalent to solving our original QP. And we can just plug in kind of by definition and compute what the dual is. And it comes out immediately from solving a quadratic formula that you get the dual problem to this minimizes over y, this finite maximum, where the first term here looks like the quadratic formula, just incorporating, c and q in some relation to y. And all of our indicator functions turn into linear functions in our radial dual. So instead of the indicator for each constraint, we now have just a simple linear function in terms of a times y. But big warning message, this dual is only meaningful when you're strictly upper radial. The fact that I could apply the definition and get this is what it equals, that's only a useful thing to us if we have this non-decreasing upper semi-continuous property. But here, it turns out that's very benign. So to get our duality to hold for this QP, you need the right-hand side vector b to be positive. We could reformulate our QP to get the right-hand side to be positive. And you need that for every feasible x, this x times qx is bigger than or equal to -1, which certainly if you were a convex QP, this q would be positive semi-definite and you would trivially have this bigger than -1. But even for some non-convex problems, our duality still applies. You can have non-convexities letting this bilinear term go all the way down to -1. So we can apply here safely, but just because we can take the dual doesn't mean that it's always useful. So here we have our reformulation, and this reformulation is really much nicer to work with. So this has things going on that the primal has nothing like. So first off, we're unconstrained. The indicator functions went away and just turned into linear functions. So instead of having to do some kind of projection onto the feasible region, we're now defined everywhere. And the kind of operation we have to do with the constraints is just this multiplication, a times y. So to evaluate all of our constraints, we'd do a matrix multiply, but that's kind of the whole cost of dealing with the constraints in this objective. Our dual is uniformly Lipschitz. And the second terms are linear, so definitely they're Lipschitz. But this first term is linear on the outside, and then everything inside that square root is quadratic in nature. And so you could check that this result from the quadratic equation is also a Lipschitz function. And so, you know, we've gotten Lipschitz continuity for free, even though our original problem had a quadratic shape. And then this third point is that we're a really simple finite maximum. So, you know, coming up with what the subgradients are of this objective is really straightforward. You know, we have a simple structure for how to optimize over it. And so we're set up, we could run the subgradient method to solve this. We have this new objective that's our transformed QP. And you could just take, you know, whatever x naught original primal solution you have, apply gamma to it to get a dual solution y naught, run updates from that y naught solving this dual problem and eventually approach dual optimality. And then if we apply gamma again, you would get back a point in the primal. You know, assuming our duality is good, that primal solution should be close to optimal if the dual solution was close to optimal. So we have, you know, we get this subgradient method. The fact that this is a simple maximum, we can do a much more clever algorithm. We could replace the objective we were dealing with that was this finite maximum by a smoothing of it. So we could have, instead of this max, you could take an exponential of each term in the maximum, add those together and take the log of the whole thing. And here I have this rescaling eta. If you take eta to 0, this quantity approaches that maximum. So you know, this is closely related. As eta becomes smaller, this is closer and closer to that maximum that is our actual dual problem. But this, you know, log sum of exponentials is a smooth function. And so we can apply accelerated smooth optimization kind of methods to it. And so solving this ends up giving a much better algorithm. And so, you know, we do the same thing, take your primal solution, apply gamma to it to get a dual place to start, run an accelerated method on this version of the dual objective, and then at the end apply gamma back to get a primal solution. And you know, for comparison, in regular primal algorithms that preserve convexity, you need some stronger operation to keep you convex. So, you know, here I've just taken some of the really most basic algorithms that preserve convexity. You could do some kind of gradient ascent on this QP. At each iteration, you have to project onto your feasible region. You could do an accelerated version of that. Or you could do this classic Frank-Wolf method that solves a linear program at each iteration. But all of those have to do some non-trivial step to stay feasible. And so that makes them much more expensive if you want to go run them on a large problem. And indeed, if I make some random quadratic programs and run these, if I have about 500,000 non-zero entries, we get that kind of all the methods are reasonable. You know, the accelerated gradient method and our smoothing method are both the best. But the iteration cost on those classic methods all grow much quicker than our algorithm. So if I take it up to having about 10 million non-zeros, all the classic algorithms really start to fail. They're having to solve some LP or, you know, even a QP to take one step, whereas our algorithms just need to do some matrix vector multiplication and then evaluate this minimum or the maximum in our objective. So, you know, we can, in a much more scalable fashion, grow up. So we're getting some good performance gains out of this reformulation. You know, really, it gives us a different angle of attack than the original primal problem would. So everything that we just saw with QPs works in general. This tool isn't built for QPs. That's not a kind of, you know, important special case. You know, more broadly than that setting, whatever constraints you have transform into gauges. In our QP, we saw that indicators turned into linear functions. That's a special case of constraints becoming gauges. Generically, objectives become Lipschitz, and things like smoothness and growth bounds are preserved when we do this operation. Yeah, we have that for any constraint you have, you know, we could write down the same indicator function we had before. And if you go through computing the radial dual of a problem like this, you get the constraint, this indicator function, turns into the Minkowski gauge of the set, which kind of geometrically looks like making a cone out of the set that grows up as you get larger. So you have to kind of spare my attempt at 3D drawing there, but you get this shape that grows out away from the origin, but it's a nice function that's defined everywhere. And so doing optimization on that function is, we can evaluate that, compute a subgradient of it, and make updates based on the gauge much more tractably than you can find a nearest neighbor in the feasible region. Lipschitz continuity, we saw that came out of nowhere in the QP. We just happened to be Lipschitz continuous after transforming. It's a more broad phenomena. So to get at that, another way we can think about these upper radial functions where our duality applies, they're exactly the functions where all the normal vectors of your hypograph point away from the origin. So here I have some f, and having this inequality hold for every normal vector is saying that all the normal vectors point out. So as long as all your normals point out, our duality holds, and that's kind of if and only if. And then if you just strengthen this a little bit, if you say that not only are all of these normals, all of these inner products are non-negative, if they're bigger than some constant r times your zeta here, then we get 1 over r Lipschitz continuity in the radial dual. What this kind of constant r is measuring is how close these normals get to the origin. So as long as the normals all point away from the origin, our duality holds. If you see how close one of the normals gets, so in this picture, that's my picture on the bottom right. In the bottom right, that's the closest normal to the origin. And so how close that gets there determines how Lipschitz you are when you transform. And so for concave functions, you can simplify this since their normals always stay outside of the hypograph, since you have a kind of convex shape there. So for concave functions, the best Lipschitz constant just comes from looking how close is an out of domain point, this f of x equals 0, to the origin. So if you look at how close something out of domain is to getting to the origin, that tells you what your Lipschitz constant would be. Which means pretty generically we have some Lipschitz constant. As long as the origin is not, right next to something out of domain, you'll have a Lipschitz constant for your concave problem. So we're kind of getting Lipschitz continuity for free out of this, which means we have everything we need to analyze the radial subgradient method we had before. So for a generic convex problem, you're maybe minimizing a function over some constraints. When we take the dual of that, the constraints just turn into a gauge, and our method then does these continually moving downhill kind of steps on this transformed problem, eventually coming back. And we get a really nice convergence theorem for this. And so the rate of convergence for this, if you choose a particular step size here, is that this radial subgradient method, after 1 over epsilon squared steps, will have relative accuracy on the order of epsilon. So it's relative in that I divided by the primal objective value, but this has entirely removed the Lipschitz constant from the convergence rate. Instead, where there used to be an m for Lipschitz constant, we now divide by r, which is this kind of radius around the origin. But we get a nice kind of rate, no bad constants show up. That pins down that this machinery works in general. Likewise, kind of going quicker here to just sketch some more of what you can do. You can have smoothness in your objective. So if you have a function with bounded level sets, so if you have your f has the things that are positive in objective value are all in some bounded region, then smoothness is preserved by this transformation. And so if your original function is L smooth, meaning it has an L Lipschitz gradient, then the radial dual is also on the order of L smooth, with some constant here that's pretty pessimistic about how much worse it could get. But smoothness is preserved taking this dual, which gives us what we need to analyze that smoothing method from before. So if you had a generic looking problem that was maximizing the minimum of a bunch of smooth functions over some polyhedral constraints. Then our radial dual is just minimizing the max of each of those things transformed. So each of the smooth functions in our primal turn into just its smooth radial dual, and the linear constraints turn into linear functions in the dual. So we now have, again, a finite maximum of terms that we're trying to minimize. We can replace that with this log exponential setup. And so this soft max gives us this nearby function where we're taking, eta here is nearly 0, which makes this nearly the same as the maximum we just had, adding up the exponential of each term. And our algorithm ran the accelerated gradient descent kind of method on this. And our theorem, putting everything inside big O, if you choose eta on the order of epsilon, then you'll get your relative accuracy here converges at a rate like 1 over epsilon. So we've gotten rid of a square from the previous result. The subgradient method was like 1 over epsilon squared. And here we can just get 1 over epsilon, which explains why this is a few orders of magnitude better back on our quadratic programming example. Now, the kind of growth bounds we had before are preserved. So all this slide is saying is if you had a growth bound with some exponent theta that holds locally around some x star, you'll have the same exponent theta in the dual problem. So whatever classic speed up you expected from this kind of growth bound also holds in the dual. We accept the same kind of speed ups will hold. So that kind of extra theory or structure carries through. We're not losing anything there. And then finally, let me check. Great. None of the real structure that we've built up till now actually needed things to be convex. We started by saying that projective transformations preserve convexity, but we don't need to be convex to apply our machinery. The constraints turning into gauges, Lipschitz continuity and smoothness, none of those results assumed convexity or concavity of the functions we're looking at. We just used those in our convergence proofs to have that we converge to an optimal solution, but the structural results didn't need convexity. And so I have just a couple non-convex examples that come out of this machinery. So if you have a non-convex set, its indicator will be upper radial. So our duality applies exactly when that set is star convex with respect to the origin. So if you have this kind of goofy, X looking set, you can still transform it and you get the same kind of gauge shape. It's now not a convex gauge because we're convexity preserving kind of if and only if. So we started with something non-convex, it'll definitely come out non-convex. But this gauge is much easier to work with than orthogonally projecting onto that non-convex set. Doing projections onto a non-convex set, you now can have multiple answers. There's not a unique closest point. And you have to, you're now having to solve a non-convex sub-problem to figure out your nearest point. Dealing with this gauge is relatively straightforward. This gauge here would be differentiable everywhere except the origin. At the origin, it's a corner, but it's something we have gradients of and could more reasonably optimize over that set without having a non-convex sub-problem to deal with. So this gives us a tractable way to go at these broader kinds of sets, as well as lots of non-convex problems. If you build them in a structured way, will still fall into our radial duality. So a typical kind of learning problem would want you to maximize the some kind of likelihood given a bunch of samples Cassie. So if you have S samples here, you might want to maximize your likelihood, or you could write this as minimizing some loss. But if you believed T of your samples were outliers and you explicitly want to remove T elements from your sample, you could directly model that by saying, well, I want to maximize my performance on the best S minus T elements. And if you set up a problem this way, the radial duality will still apply to this kind of outlier removal, even though that makes the problem non-convex, provided each of our original F functions was upper radial. So if you built this out of some least squares model or some typical kind of likelihood function that's convex on each term, then you get the same kind of thing here, where more broadly, this upper radialness is preserved under minimums and maximums and sums and rescalings. So many operations you could build this out of all stay nice and well behaved. So you can tackle lots of non-convex things where this dual still applies, as well as lots of non-convex regularization. Those are all centered at the origin in a sense. And so they're very structured about the origin kind of by default if you have some regularization term. So without really any work needed, you'll get that those fit well in being upper radial. They're already symmetric about the origin. But all of that kind of projective transformation work to say that orthogonal projections are expensive, and we have a way to get around that. So you can transform those away. But thank you all very much. My Google Assistant just told me it was 2 o'clock, so I have fully exhausted an hour. So thank you. I'm sorry for going so long.
Thank you, Ben. So, any questions from the audience?
I guess I could start. Oh, from the audience, you mean not the committee?
No, the committee is fine.
Okay, I see. I guess I'll ask one quick question. So this is the star convexity thing is really interesting. I mean, it gets me thinking about low rank optimization, and low rank projection involves an SDP if you want to project the set of low rank matrices. I mean, in any case, whenever you have a cone, you have some sort of star convexity property as well. So that's what I'm wondering whether what is the operation that you would replace projection onto the set of low rank matrices with?
Yeah, so it if done directly, it ends up being pretty unsatisfying. So if you had a low rank matrix, that non-convex set is really a collection of kind of linear spaces. Easier to see if we talked about sparsity. If you wanted something to have only 5 non-zero elements, and if you look at the set of things with only 5 non-zero elements, you can make that a star convex kind of function. When you transform it, you don't get anything more enlightening. In essence, you would have had an indicator that was 0 in all the things that were sparse or low rank, and infinity elsewhere. The indicator flips over in essence. It still turns into an indicator when you have these size 0 sets. Kind of the reason it doesn't turn into a nice gauge is that we need this radius. And the better answer is that we're well structured when we have this radius around the origin. It's kind of some region where everything is nice. You don't have normals cutting really close to it. These sparse or low rank sets are razor thin. You're not going to get a ball inside of them. And so to get a gauge that has some width to it, you need to have this nice ball inside your feasible region that those sets don't have. And so when you transform them, they'll have infinitely sharp gauges, which looks like an indicator function. So it falls short if you go at it directly. If you use something like some non-convex regularization that spaces it out more, so instead of going all the way to a 0 norm to get sparsity, you could use a kind of Q norm between 0 and 1. And then all of a sudden you can have nice space inside your sparsity inducer. But you need to do something that lets you draw a ball inside of your regularization.
So just to follow up on that really quick, what if you did a Q norm on the singular values of a matrix?
Mm-hmm.
what, I mean, if you look at the Q norm ball and the singular values,
Yeah.
what would you get in that case? Any sense that it would be easier?
Yeah. You'll get some gauge that actually looks not too different than this kind of thing. So and it'll have you'll get some gauge that has kind of veins sticking out towards each of the extreme points of this cue ball. So you'll have some gauge that comes out looking like that. Numerically getting at it, I don't know if that will have a closed form. So it'll, if you were just doing a Q norm, it turns into some polynomial root finding in one dimension. So that'll be some eigenvalue problem to solve in whatever higher dimension or whatever matrix space. But doing some maximum eigenvalue problem is still going to be cheaper than computing some kind of full SVD and doing some approximation of projecting.
And Ben, could I, while you're on this bit of the thesis, could I ask a couple of kind of obvious duality kind of questions that are the kind of along the lines that you might ask about any kind of dual thinking, which is, so one is interpreting the dual variables and, whether there's an interpretation, and the other is, I mean, is there any context in which one might think of primal dual kind of algorithms?
Yeah, so in interpreting them, in some sense, this kind of dual goes a different direction than a classic, like Fenchel duality, where there your problem is kind of based on this conjugate vector space, and you're doing some problem to define your classic dual that's kind of this full dimension subproblem. Here, our dual is defined as just this one-dimensional thing. So the kind of soup defining this dual is just doing a one-dimensional subproblem. So there's not the same level of, in a sense, mixing of information, where a classic dual, one point in the dual says something globally about the primal. Here, we're not doing some full dimension subproblem in computing this. It's only capturing, up to one dimension of the geometry. Really, it's kind of capturing no dimension of the geometry because we have a bijection between the primal and dual. So the primal epigraph is exactly this gamma applied to the dual hypograph.
Right, I'm just wondering what that number actually means. I mean,
I don't have a good interpretation kind of beyond that. It's just a reshaping. So it captures exactly the same local information. So the gradient at that point is just a function of the original problem's gradient at the associated point. So really, the information's preserved. It's more akin to a pre-processing or preconditioning of your problem that changes the geometry, but doesn't fundamentally move the points around. You have the same local neighborhoods. Then giving primal dual methods, in a sense, there's the place where that could be reasonable is if you had things in your primal that you really liked. So if you had some sets that were easy to project onto, I think the easiest way to make a kind of primal dual method would be to do some part of your updating in the dual, but I can always apply gamma to come back to the primal. So I could do some steps on gauges in the dual, get back the primal solution, and then do an orthogonal projection in the primal with your box constraints that you like a lot. Because kind of there's going back and forth is equivalent. The local information is the same. And so if there are primal operations you want to keep, in theory, those could be done separately. And you make some descent on the dual and come back to the primal. But the analysis details of that, I'm not sure what shape that would take. But some other like primal dual kind of things you can do if the duality doesn't hold here, I was on the right slide, you could take this twice and you get something like a closure of the objective. So there's, there's some kind of star convex closure of your set. You weren't star convex, and so the duality didn't apply. But if you do this operation twice, you get the star convex function that surrounds your original function. Kind of like the convex conjugate gives the convex envelope if you do it twice. So some similar things like that pull through.